Right, I've drawn a glulam cross-section.
Yep.
And I've got a couple of questions here, which I will ask in order. I'll let you finish answering them.
Yeah,
before
so
I
we'll
ask the next
reserve
one.
this section will reserve for Callum's questions. If he thinks of something, he can write it here, rather than interrupting my train of thought, because I can only think about one thing at once.
It's
okay?
the way my mind works, I'm so sorry.
Right, so your first question was, can I explain better how the stress distribution is? So we were looking at the cross-section of the glulam, and it might be clearer actually if I draw the longitudinal, because the stresses are axial stresses. So when I drew the graph, I was drawing the stresses that are in the direction of the glass that we're drawing on.
Out towards the audience.
Yeah. So if I draw the glulam lengthways, I can draw the graph with the orientation in the same way that the stresses are actually going.
Can I interrupt you?
Yeah. Do you want me to do it bigger?
I don't know what an axial stress is.
Okay. Right.
What does that mean?
Right. So if you have a piece of wood and you're pushing along the axis of the member, which is usually along the grain, because the axis of the member is usually oriented more or less along the grain. If you're pushing, that's compression. If you're pulling, that's tension. If those forces are going along the axis of the member, we call that axial force.
Okay.
If it's a force that's running perpendicular to that, we call it a transverse force. So if we draw an element of material, so we take a piece of this beam, and it's just like a cube that we've taken out, a really tiny cube, and we think about the stresses that can act on this surface. We divide the stresses up into two types. One type is called a normal force, which is acting at 90 degrees to the surface, and one is called a shear force, which is acting along the plane of the surface. And these forces are stresses in reality. Often we will talk about stresses as if they were internal forces, but in reality they're stresses, they're pressures on the material.
Okay.
So a shear stress is a pressure going along in the direction of the surface, and a normal force is pushing down.
Okay.
It's like pushing down on the surface or pulling up.
Okay.
So this can be tension or compression. Those are the two types of axial force. And the shear force can be in whatever direction.
Okay.
And they result in a complex thing of stresses
I've made him
that
go
I
off
don't want to
topic.
go into.
And
no, but
I'm really going to make him go off topic after this. I have to write this down because I'll forget.
Quake. Oh, what made you think of that? Anyway, so when the beam is in equilibrium, static equilibrium, right, the forces are balanced, the beam is not moving, it's not in motion, then the system of stresses that we have on this small cube must balance. So if there is tension on this face, then there must be equal and opposite tension on that one. If there is compression on that face, there must be equal and opposite compression.
Otherwise it's going to move.
On that one, it must be in equilibrium. And the same with the shear forces as well, because the shear forces are wanting to cause rotation. So there must be a balancing shear force on the other side that stops that. So everything kind of has to be in equilibrium.
If I think back to my school days, I'm thinking Newtonian mechanics. Is this correct?
Yeah, you can do this with simple Newton kind of thinking. And what you do is if you're scaling this small element up to the big scale, you imagine that there are small differences from one side to the other, and that will allow you then to calculate actually the shape of the distribution.
Okay. Which brings us back to stress distribution.
Yeah, so if the beam is carrying forces, we can take an element out, like a strip out, like this cross-section. We can imagine there's we've cut an imaginary piece out of the beam, and we can look at equilibrium equation on this cross-section. So
equilibrium equation, what does that mean?
Well, not in motion.
Okay.
All so of the forces that are resulting from the
there.
stresses, can balance out.
Okay.
So if this is a beam that's loaded with, this is how we draw, genuinely how we draw a uniform load.
All right. I could do that.
Yeah. And it's supported.
I thought it was difficult.
There and there. What we would do is we would look at that force, and the combined effect of that force, and if it's uniform, it's acting in the middle, and we would resolve on that surface, we would resolve for equilibrium in the up and down direction, the side to side direction, and the rotation direction, and that kind of allows you to calculate the forces that are acting on a.
Right.
If you wanna look at it, and we don't really have time to do it, it's just called engineer's beam bounding theory.
I've heard of that.
Yeah.
But one of the questions when you did the diagram, you were showing this stress distribution. Is that right? What you'd call it across the whole section, and then you were saying something about the glue lines. So that's the bit I think we need to.
Yes. So let's draw the simple case, which is a pure bending. So there is no shear force in the beam; it's just bending action. And you get that kind of. I'm stopping you asking any more questions by drawing here. That's my tactic. If we have 4-point bending, which is a common way of doing the tests on timber, in between here we have no shear force, because the shear force pushes up on that one, and this force is equal and opposite to that one, so the shear force disappears for this middle bit. We've just got pure bending moment.
So this is the situation we are considering.
Yeah.
Okay.
So what we're trying to balance in our free body diagram, which is the element cut out.
Free body diagram.
Yeah.
Keep going.
Equilibrium.
Okay.
Yeah. The forces that we're trying to balance are just these turning forces.
Okay.
And the turning forces are balanced by basically if you have a force acting at a distance from a point and something is rotating by a point, you can calculate the moment, we call it.
Yeah.
It's the turning action of that force as the multiple of the force times the distance.
Yeah.
So you kind of work everything out, and basically for the point of view of the forces, the turning point turns out to be in the middle of the beam.
Okay.
And the force that's acting as the equivalent sum of all of the stresses in this lamella is acting at a small distance, and the force that's acting as the sum of all of the stresses in this lamella is acting at a longer distance. So it turns out that there ends up to be more contribution to the resisting the bending action in the top lamella. You end up with higher stresses.
Okay. Can I just, how are you loading this? Are you still loading it that way?
No, it's in bending.
Diagram?
Yeah. So actually, if the direction of the stresses is in this direction, it's axial.
Okay.
So we have
you're
in
just
this.
illustrating it with that.
Yeah. So we have compression in the top,
Got you.
tension in the bottom.
Okay. Which is why I should have drawn it like that.
Yeah,
Rather
I
than
can't.
like
There's a sign convention. It's strictly speaking, you should decide which side is compression and which is tension, and I've forgotten what convention I've been using.
Mm-hmm.
But basically, you end up with a triangular system.
So here we have tension, and here we have compression.
Tension.
Oh, sorry. Yes.
Compression.
Yes.
Yeah, I mix it up as well.
Yeah.
Don't worry. So we've got zero axial force on the middle, compression on the top side of this bending beam, and tension on the bottom.
And this would be considered to be an idealised diagram.
Yes.
Because
if there is variation in the material stiffness, then they won't share the stresses in such an equal way. There will be some slight differences.
Yeah. Variation in material, if we ignore the wood and consider it to be a homogeneous isotropic material just for a moment, means the glue line in this case, which is not going to have the same mechanical performance as the timber.
If it was steel and we had a like magic glue that glued steel together as if the thickness of the glue wasn't there,
right,
then you would end up still with this triangular thing, because it's the properties of the lamellas actually that is really the
so then
thing.
The interface, you've kind of got rid of the interface in this.
Yeah, we're sort of ignoring the effect of the interface in this simple example.
Yeah.
But what would cause a difference is if you had different stiffnesses of the lamellas.
Right.
And you would, because it's wood, so each piece of timber
but I mean, that's going to be kind of
different.
randomised, isn't it?
It is for what's called homogeneous. No, it's not called homogeneous. It's called, It is called homogeneous. Homogeneous glulam is where all of the pieces are the same grade, so we're assuming that they're all randomly equivalent.
So the timber before it goes into glulam is going to be graded?
Yes.
Always? Always, always, always?
Strictly according to the standard?
Yes.
Yes. It's the European standard, yeah.
Because of that, the glulam will be predictable, or do you have to then test the glulam afterwards?
You can do either, actually. So normally you would look at the grade of the lamellas that you put in and use the process in the standard to work out what grade of glulam that results in. Okay. No need to do any testing. But the standard does allow you to do testing if you want. Mm-hmm. So for homogeneous glulam, where they're all the same grade, that's quite a simple process. But you are allowed to do something called combined glulam, which is where you can have different grades or strength classes in the different lamellas.
I was going to ask that.
Yeah, so because the top and the bottom are more important in carrying the load.
Compression?
If it's bending that way.
Yeah.
Yeah. I mean, it's not always the case that the beam is bending, sagging.
That's not what it makes it more complicated.
Yeah, so you can...
I'm just trying to remind myself.
Yeah. Normally, you have compression, but if the beam is hogging, you can have tension up there. But yeah, normally it's compression. Compression.
So you're talking about, we've stress graded the timber, but we got like some C24 and some C16. We'll put the C16 in the middle and the C24 on the outside.
Exactly, yeah. That would be a sensible thing to do.
Yep.
Because on average, the C24 is a little bit stronger and stiffer than the C16.
That leads to another question.
So you get more benefit putting it on the outside than in the middle.
Yes, I get that.
And in fact, because if you know that this is definitely going to be in tension, then you can even put what you think is the best board on the bottom.
How do you know? How would you define best board if it's both C24? Is that just going too far off piece? Best board. This is
well,
really
it might be like this. It could be like another grade, like it could be C30.
Okay, that's fine. But I haven't finished.
Let me finish. Let me finish my thought. Yeah. So if you have a board with knots, you would think probably that will be less strong in tension than a board without. Mm-hmm. So if you have a choice, you would put the knots at the top because knots don't have much effect on the compression strength, and put the one without the knots here because knots probably or likely might have an effect on the tension strength. And in that case, you would have an upside down, a possibility of installing the beam.
So there's a right way up and a wrong way up.
There would be,
Normally there isn't. Is that right?
Normally there isn't.
Well, certainly with this. Would that matter which way up I put that normally? If it was all C16, would it matter which way up I put it?
No.
Okay. Can I ask that question now, or are you still...
What was your question?
Well, I haven't asked it yet.
Okay. Right.
You stopped me. No, if I...